Welcome to Academy.com. In advanced calculus, let us discuss about axiomatic approach on real number system. The number system can be built up logically starting from a basic set of axioms or self-evident truths, usually taken from experience. There are many different system of axioms, but one that provides a foundation for many others is that of the real numbers. These axioms consist of statements about the real numbers and the relationship between them. Now we will discuss one by one about axiomatic foundation of the real number system now. Your first one, point sets and intervals. Point sets intervals. Consider the statement like A is lesser or equal to X, lesser or equal to B, which means the set is a number between A to B included A and B. Here, this can be closed interval. There, closed interval both sides. How to represent this? You have to use the braced bracket A, comma B. Both sides closed. Next statement, look at here. A is lesser to X, lesser to B, which gives open interval. Which is represented by AB. Now, another set like here, A lesser X, lesser or equal to B, and A is lesser or equal to X, lesser to B. Here, which represented by here, this open A, comma B, this closed. Here, A is closed with B open. These are called half closed intervals. Half closed intervals, because one side closed, one side open. Now, for example, look at here. Here, modulus X, or here, suppose it's less than 4. How to represent its bounded set like here, minus 4 is lesser equal to plus 4. Then, so it's represented by minus 4 to 4. Next, so generally you can say minus infinity lesser to X plus infinity is represent all real numbers. All real numbers. Next is countability. What is countability? A set is called countable or numerable if its element can be placed one-to-one correspondence with the natural numbers. That is, a set is called countable or numerable. countable or denumerable if its elements can be placed in one-to-one correspondence. One-to-one correspondence with the next number. With these are called countability. For example, look at here, given 1, 3, 5, 7, 9, like natural numbers. One, two, three, 4, 5. Here, what do you mean it? Here, both are one-to-one correspondent. Means a set is infinite if it can be placed one-to-one correspond with a number set. An infinite set which is countable is called countable infinite. Here, one-to-one correspond. Here, regarding the natural numbers 1, the given number is 1. 2, second number is 3, which means it's a set of odd numbers, odd natural numbers is countable. Means 1, 3, 5, 7, 9 up to infinity it goes. This is one-to-one correspondence, so it can be counted. One, first number, second number, third number, like. Next is neighborhoods. Neighborhoods. What do you mean it? Yeah, the set of all points x such that set x is such that x minus a is lesser to delta, where delta is positive, is called neighborhood, where is called neighborhood of the point A, of the point A. The set of all points x is such that means here you can say 0 is lesser to x minus a is lesser to delta, which x is equal to a is excluded, is called deleted delta. Here, this is a set of x minus a modulus that is greater than 0 and lesser than 2 delta. Absolute of x minus a is greater than 0, and that means we can say, so x can be greater than, so x minus a is greater than 0 and lesser than delta is called neighborhoods. Next is limit points. What is limit point? A limit point, that is point of accumulation or cluster point of set of numbers, is a delta number L, such that every deleted delta neighborhood of L contains numbers of the set, that is, no matter how small the radius of the ball about L, there are points of the set within it. Here, for example, here the set of rational numbers is not a closed set, since, for example, look at root 2 is not a number of that set, because in natural number root 2 will not come. It's because of its irrational. Therefore, you can say 0 is lesser or equal to x, lesser or equal to 1 is closed set in real numbers, because here x is greater than or equal to 1 and lesser than or equal to, greater than or equal to 0, lesser than or equal to 1 means it's a decimal representation. In that, in a closed set here, root 2 is not the element of this closed set, because root 2 is irrational, because we consider a rational set. Next is Bolzano-Weierstrass theorem. Bolzano-Weierstrass. What is it? It represents, it states that every bounded infinite set has at least one limit point. Next one, algebraic and transcendental numbers. Algebraic and transcendental. Transcendental numbers. First, a number x is a solution of a polynomial if x is a, x means a number, x is solution of a polynomial equation what is polynomial equation in general form? A0 x power n plus a1 x power 1 plus a2 x2, like it goes, a n minus 1 x power n minus 1 a n minus 1 x plus a n equals 0, where a n is not equal to 0 and integers, and a1, a2, a3 are integers. This is called a polynomial, or the degree of the equation, polynomial equations, where n is a degree of that equation and n is degree of the equation, degree of the polynomial equation. Now, look at here. For example, 2 by 3 is 2 by 5 is a solution of 2x minus 5. We know that 2 by 5 is a solution of because if you solve 2x minus 5 equals 0, that is 2x equal to 5, x equal to 5 over x equal to so 5x minus 2, 5x. Here 2 over 5 is a solution of 5x minus 2 equals 0 since 5x equal to 2 and x equal to 2 over 5 is a solution. Therefore, this is therefore you can say 2 by 5 is a transcendental number because it's a solution of a linear equation that such that it's a polynomial equation degree 1 which is expressible, that is this equation has a solution 2 over 5, so it's called a transcendental, no, it's called a algebraic equation. Next one, for transcendental, the set of algebraic numbers is a countably infinite, but the set of transcendental numbers is not countably infinite. That means some numbers cannot be expressed as a solution of a polynomial equation. It is called transcendental equation. Transcendental equation number. Some numbers cannot be expressed as solution of your polynomial equation is called transcendental numbers. Next one, complex numbers. We know that here, suppose consider x squared plus 1 equal to 0 is a polynomial equation which gives the solution x squared equal to minus 1 and x equal to square root of minus 1 is, that is square root of a negative number is not a real number, so it is a complex number, so which can be expressed I, that is x has the solution of I. Square root of minus 1 equal to I is a solution. Then therefore you can say a plus bi is a complex number where a and b are real numbers, where a comma b are real number. Then the two components is there. This is a is a real part, a plus bi. This is a real part. This is imaginary part. Now, modulus of a complex number a plus bi can be represented by square root of real part square plus imaginary part square. Next, simply you can explain for the detailed doing coming videos. Now, here consider polar form of complex number. The polar form of complex number can be expressed, suppose z equal x plus IOE is a complex number which can be expressed 4 times cos phi plus I sin phi. We call a polar form of complex number. Now nth root of z can be expressed in polar form, that is z 1 over n is equal rho cos phi plus I sin phi over 1 over n, which is equal rho over 1 over n cos of phi plus 2k pi over n plus I sin phi plus 2k pi over n, where k equal 0, 1, 2, 3 up to n minus 1. Further, we can express a complex number, that is e power I phi equal cos phi plus I sin phi. Is Euler formula. And that e equal approximate to 0.7171828. It continues to square. That is continental number. So far we discussed about numbers, axiomatic approach of that numbers. Now in further videos we will discuss about that advanced calculus one by one. We have done. Please subscribe our YouTube channel.